We're recording.
That was amazing.
Okay. All right. Wolfgang.
Yes.
Give me a howl. You let your locks down, man. I think we should hear that. Well, let's see if you.
What is that?
Do it, Wolfgang. I'm not going to lecture until you do it. Do it. Nice. That was awesome. Okay. All right. Okay, we have a lot to get through today. We're going to get through some good stuff. Follow up from the end of last lecture, an item that I didn't get to that we've kind of got to get through. So the gamma mu matrices that we introduced last time, remember we introduced these so that we could figure out how the Lorentz transformations would actually act on a spinor. So we use these gamma matrices to construct the, or commutators of the gamma matrices act as generators when you're building up transformations as they act on spinors. But these gamma mu matrices are going to be very ubiquitous throughout the course. We're going to see them a lot, so you're going to get comfortable with them. You've got some exercises in your homework to play around with various properties that they have. But there's something that is very interesting about these, which we could ask is, how do these transform? And there's an interesting answer to this, which is actually going to give you a sense of relief. Okay, so initially this is going to be kind of ugly, but in the end it's actually going to be really pretty. So just bear with me. So first of all, grab a card for some victims. Connor, where are you?
Which one?
Here.
Yep.
Connor, what kind of object is this? If you're just going to like kind of describe its properties a little bit. It's a matrix in what?
40.
In 4D space-time?
Yeah. Or
Brooks is willing to help you out. Throw him a bone, Brooks.
Spin space?
In spin space. So it's a matrix in spin space, but in space-time it's only got one index. So it's kind of like a vector in space-time, but it's a matrix in spin space. So what I want to do first is kind of consolidate this and be able to say this is just acting like a vector in space-time. So watch how this happens. So first of all, let's actually, for once in the course, and then we'll never do it again, let's actually index spin space. So if I were going to throw indices on something as it acts in spin space, then I might say something like the following. Let's see. Yeah, that's exactly what I want to do. Okay, yeah. So first of all, we know that psi goes to psi prime, and then there's going to be something which acts on psi to give me the new psi prime. And if psi is a spinor, then I'm going to give it a spin index. Okay, so this A goes from 1 to 4 over the 4 dimensions of spin space, and that's not the dimensions of space-time. And then what I'm going to do is I'm going to call the transformation of the spinor by something S lambda, and then I'm just going to give it an index structure so that we can use the summation convention as we're used to do this. Now this thing is secretly that e to the I over 4 sigma mu nu omega mu nu, where the sigma mu nu's are built from commutators of the gamma matrices. Right now all I'm doing is I'm consolidating it so that I don't have to write this all the time. And so I'm calling it this element S of lambda. And the reason I'm calling it S of lambda is, first of all, this is not lambda A prime A, where this is a Lorentz transformation matrix. Because those don't act on spinors. Those act on tensors. So we don't want to write that. So instead I'm going to call it S, but S is specified once I say what transformation I'm doing. So if I say I'm doing a rotation in the xy plane, there's a lambda for that, and there's a corresponding s for that. So if I specify the lambda, I'm also specifying the s, although there's a little bit of work you have to do to figure out what the s matrix would look like. So, and then all I'm doing here is saying this matrix acts on a 4-component spinor, so it's got to be a 4x4 matrix, and I'm indexing the entries of that matrix by A prime and A. Okay, so, oh yeah, a piece of notation that I left off from the end of last lecture, which I need to go ahead and get over, is the following. So at last lecture, we discovered that the dual that we need to use in order to build invariants is actually given by I gamma 0 psi. So we found that the metric we need in order to build our dual spinors is I gamma 0. And we talked a little bit about why that was the case, and you've got an exercise in the homework to prove why you need this, or a part of why you need this. So what we're going to do is introduce a piece of notation which is the norm in the literature. So we know that we normally take psi twiddle and we dagger it, and then psi twiddle dagger psi is what is invariant. So what we're going to do is we're going to take psi twiddle dagger, okay, which is of course just I gamma 0 psi dagger, and we're going to give that a new name. We're going to call it Sidebar. So going forward, if I want to write an invariant out of spinors, I'll just write it as Sidebar psi. So henceforth, I'm going to keep writing sidebar, and when I write sidebar, I'm just talking about this object right here. Okay, which you can go back and unpack and match it up to the notation we were talking about with dual representations and taking transposes and so forth to form invariants. Okay, so this is an important new piece of notation. Okay, now with that in mind, if a spinor transforms like this, then since psi bar is defined in terms of the spinor, you can deduce how psi bar would transform, and you'll find that psi bar transforms like this. In a manner similar to how we notated transformations for vectors and dual vectors. Okay, so we're giving this a lower index because we're referring to it as a dual spinor. So just like a dual vector gets a lower index, the dual spinor gets one, and so forth and so on. Okay, and then the invariance of psi bar psi arises because if I transform both of these, then I basically have psi bar s lambda b prime s lambda. This is going to look weird, but b prime a psi, and then this is going to have a b index, and this is going to have an a index. And that was a poor choice of spacing. But if you take those two things, again, our notation is such that if this is the original transformation, this is just the inverse. And so when I combine these two things, these just actually give me delta, or the identity on B and A. So that just says, if this is A, make it B. And then you have exactly what you started with. Okay? So I'm just acknowledging that this transformation is the inverse of that transformation, which is what we expect. Okay? All right. So now coming back to gamma, gamma is something which is going to act on a spinor. And so we might anticipate that if we were going to labelize gamma, we might give it an upper index and a lower index, and that way, if it acts on a spinor with some upper index B, then it's just going to create another spinor with an upper index A. And then what we can do is to figure out how this transform, we just transform every single index on this thing. So we would say, let me give myself some room, that gamma mu A B goes to gamma mu prime A prime B prime, where we know how this index transforms. That's just a lambda matrix. And then these A primes and B primes just have the transformation properties that I've written down here. Okay, because a spinor index transforms according to this rule, and a dual spinor index transforms according to this rule, and this has just got one of each. Okay? So if I do that, then I'm going to find that I need a lambda mu prime mu to transform that index. And then I'll need one of these S lambdas to transform the A index, and an S lambda B prime to transform this index. And I just moved this one over so that we could, if we wanted to use matrix multiplication, we would have to get the B here. The B's adjacent, okay? So again, this is going to be some technical details, and it's going to be followed by a, whew, I'm glad we don't have to think about that anymore moment, okay? So at the moment, this is the transformation rule for a gamma. Okay? Yeah, Ariel.
We're treating the mu as just a space-time index.
Oh, it is a space-time index. It is a space-time index. Remember, we found the gammas by solving this Clifford algebra, where this is the metric of space-time, so those are space-time indices, and so too are the labels on the gammas. But these are 4x4 matrices in spin space, and that's why I need that identity in spin space for this expression to make sense. Okay. All right, so now the important observation that comes out of this is that we are never going to have some weird object in spin space just sitting there, because we're going to want to build our Lagrangian interactions, whatever we're working with, in terms of invariants. Okay? So we might, for example, have a term like this in a Lagrangian, because this is invariant. But then we might also consider a term of the following form. Where is it? Yeah. Okay, so we have sidebar psi as an invariant, but we could also consider shoving in a matrix in spin space, say gamma mu. Because if you sort of think about it, this is like our standard vector magnitude. You know, you think of this as a row vector or a column vector. This is a row vector. You combine these two things, you get a scalar. But you could always separate these two things and throw a nice square matrix in between them, and it doesn't really screw anything up, right? So too here, this we could treat as a column vector in spin space. This is a row vector in spin space. There's nothing stopping us from shoving a matrix in spin space in there. Okay? And what we find is that this is in fact invariant, and it's invariant precisely because of this transformation rule combined with those. So let's actually look at how that pans out. So if I give this an index, I give this an index. Okay, notice all the spin indices go away. That's one way to recognize that it's an invariant. But if I transformed it, I would notice that transforming this guy is going to give me, where is it? Yeah, lambda mu prime mu s lambda. Oh my God, I'm never going to get these to work. I'm going to go back and fill those in a moment. Gamma mu some stuff s. Okay, this is going to be an exercise in assigning indices after the fact. Yes, that's my gamma transformation, and then I'm going to transform this guy. Psi B. Okay. Yeah, no, I don't have it written down on my paper. Oh, that sucks. Okay, I'm not gonna worry about the indices. Because I'm never gonna get the indices to work, to be truthful. There's just too damn many of them. So I'm going to disappear my indices, and I'm just going to realize that Sidebar transforms with an inverse. Gamma transforms with an S and an S inverse. So that's an S inverse. And then psi transforms with an S, okay? So if we look at this, we notice, hey, there's the identity. And what's really nice about this thing right here is that even though it is a tensor, or not a tensor, but a matrix in space-time, what is it in spin space? You could just throw the identity on there if you wanted to, or you could just treat it like a constant, same difference. So this I could actually pull out of the whole expression, and then this guy would cancel this guy. And so what I find at the end of the day is that I have this transformation rule for this combination, where I'm giving up on indices. The spin indices suck. Okay? Now, I said there's kind of a bottom line takeaway, and Wolfgang is going to be so happy to point out what kind of object is this?
Scalar.
Ashley?
It's a tensor.
What kind of tensor?
Space-time.
I like it. You can just throw words in that can't be wrong, and it'll all work out. Joe Bales. What kind of object is this?
Yeah, I generally have no idea.
Okay, I will give you guys a hint.
Please do.
If we're identifying things by how they transform, I've seen a transformation rule that looks like this.
So you're saying that the spinners,
I'm asking you, what is this thing?
that would be a vector.
That's a vector. If I squint my eyes and sort of ignore that this is some really big fancy name of something, I have something goes to a lambda mu prime mu times what I started with. What kind of object is this?
Vector.
It's a vector.
Gotcha.
Okay? So what we've done is, starting with spinners and things that act in spin space, by forming this combination, we've created a space-time vector. And then what we could do if we wanted is we could take this very sophisticated object and we could combine it with a dual vector to create a scalar in space-time. So this would be an invariant, but you would have a lot of rich structure coming from spin space in the little bits that make this up.
That object's not invariant unless you have a dual vector also.
Yeah, so this is not invariant itself, it's a vector. It transforms. But I could create, but my point is that its only transformation property is as a vector in space-time. I do not have to worry about all this spin space crap anymore. Okay, so the theme, the takeaway from this, which is so nice, is the following. If we are going to deal with invariants in this course, build our Lagrangians and so forth out of invariants, we are always working with spinor sandwiches. That is, we will always have a dual spinor, something, and a spinor, and then as long as we have that kind of sandwich, the transformation rule is just governed by the indices, the space-time indices that I see. I do not have to worry about the spinor indices. They're all taken care of as long as I work with spinor sandwiches. Joe?
So does that essentially say that the spinners give you more insight into what's going on, but they don't actually affect the space-time matrices?
No, what I'm saying is that so at the end of the day, we're always going to be interested in forming invariants. We know how to form invariants for things that have space-time indices. Now we're moving on to how do we form invariants out of things that are spinors or spinorial in their nature. And early on, when I first started talking about spinors, I said we're never going to use spinor indices. And that might have worried you because for space-time quantities, if I just wrote this without any indices, you wouldn't know if it was invariant or not. But if we give it indices, then you can look at it and say that's invariant because all the indices are contracted. They go away when you sum. But if I'm not showing you the spinor indices, how do you know? And what I'm trying to show you is that our rule of thumb will be, as long as I have a dual spinor, any operator in spin space, and then a spinor, all of the spin indices are taken care of to make this thing invariant for spin space, and then I have to then just worry about the space-time index to get a total invariant. So this is a way of us not having to deal with those spinor indices. Yes?
Okay, so 2 questions. On the transformation for gamma with the spin indices, the box, yeah, couldn't you just commute the 2 S's and then those are a delta BA and then you're done? Like you did before?
No, because before when I made them a delta BA, this index was the same as that index.
What?
Yeah.
Why though? Go back and look at that.
Yeah, go back and look at it. But these 2 things are, they're not, I agree with you. If I had written an A here and an A there, then that would have become a delta function on A prime and B prime. But those are distinct.
Okay. And then my other question was, this is assuming that all spinors are 1-1 tensors, that they have a dual index and a...
No, well, not 1-1 tensor. Just stay away from the word tensor. So spinors are either spinors with an upper spin index or dual spinors with a lower spin index. And then the gamma matrices have 1 up and 1 down. We're not going to worry about anything more complicated than that as far as spinors go. For space-time indices, yes, we have lots of weird things. Like the Riemann curvature tensor has 1 vector and 3 dual vector indices, but we're not going to see things like that in the context of spinors. Okay, how are we doing? We good? Are you now completely 100% total comfortable with relativistic spinors? Raise your hand if you're comfortable with relativistic spinors. Let me count. Just kidding. Ariel.
Yeah, I guess, why did we have this as a B prime for some order earlier? Why did we change the index from A to a B prime as opposed to an A to A prime?
Oh man, you're good. Why couldn't you guys have fought me before I erased all this? Okay, so if I enact the transformation on psi prime and give this an index, this an index, this is a, so now I can actually do this. I can say A prime, and then I'm going to have that this is actually just Sidebar S lambda psi, and I want this to be built out of those, and I want this thing to start with this and make it into an A prime. Hold on. And then I want to take this and turn it into an A prime. So you might be tempted to write this, okay? Because this A would contract with that and return an A prime. Bam. This A would contract with that and give you back a lower A prime. Bam. But we don't like expressions like this because this has got A. Which of those A's you pair up when you're summing? So the way that we get around that is we say, well, it doesn't matter what we call this because it's going to be summed anyway. Let's just call it B. I would not take this A, turn it into a B, and then turn this thing into a B, because that's actually changing something. When I write this expression, I wrote it thinking I was going to sum this over this and this over this, so let's just change the name of this one to keep it distinct from that. And that, Spencer, you'll notice, is A prime and A prime, and then A and B. Okay? But here it's a different thing. you're literally transforming two distinct indices. Here you're transforming a summed index. All right? Any other questions? So this is hard, and it takes time to digest it. And the truth is that when we work problems later on, when we start doing calculations, we're never really going to have to get into a lot of the guts of this, because this observation right here, we're going to make use of. As long as I make my sandwiches all the time, I'm consistently a good sandwich maker, then I don't actually have to worry about a lot of this spin, space, index manipulation stuff. Okay? Joe?
Very sorry. So does this mean that in this sort of situation, if you were to actually multiply things out, you would apply the dual spinner to the gamma mu matrix and then apply your dual vector? Or does the dual vector, the space-time dual vector there, multiply through the spinner, ignore the spinner, essentially commute with the spinner?
Where are we looking at? Here?
Up left from that.
Here?
That thing. All the way through.
Oh, this.
Yes.
Oh, yeah, no. So what you would do here, it technically doesn't matter how you do it, because what this symbol is going to do is it's going to take a component of this and match it to a component of this, and then the next component matched with the next component, and it's going to add them together, and it's going to do 4 of those, because there's 4 values of this and this.
So the spinors are basically constants in that?
In spin space, this is a constant.
True, and in space-time, the spinors are constants?
Well, because we're making a spinner sandwich, in space-time, this just ends up being a number. So it doesn't matter in that sense. You could treat this like a constant spin space and move it inside of here if you wanted.
Gotcha. All right.
Yeah.
Thank you.
You totally could. Okay. So look, to finish up on what I was saying, this kind of material, you do not walk out of a lecture and go, yeah, I got it. You go and you start the homework and you get stuck. And you slam the desk a few times, you go have a cup of tea, you come back, you eventually get some level of comfort with it. It's never going to be completely comfortable, bless you, it's never going to be completely comfortable, but you've got to go through the homework on this, okay? Nothing this new and abstract is ever going to feel right, just hearing me up here yap about it. Okay. And again, I don't want to scare people away. There's a lot of formalism that I'm talking about that will sort of fade away. So to give you an example, when we took GR, we did this whole exposition on how to write a vector in terms of its components and a basis of dual one forms. And then I talked about what these things were, and we looked at how everything transforms, and at the end of the day we said, you know what, we're just going to forget about everything except for those, because everything takes care of itself. And then you never thought about it again. Same kind of thing going on here with spinors. There's a functional level of comfort you have to get to, and sometimes the underpinnings are not that crucial. All right, are we ready?
Yeah.
Lights, camera. So there has got to be a physics t-shirt out there that does that. Okay, so we're going to completely shift gears now, and we're going to now start trying to talk about mechanics. Okay, we've got tensors on the table, which we know are going to be important for describing kinematic quantities like momentum and forward velocity and so forth. Also, other things that are vectors in space-time we'll discover, like photons and so forth. We also know roughly how to describe spinors. Now what we want to do is actually start writing down expressions or principles that govern how things behave. And it turns out that when you start writing down systems of mechanics, you all are familiar with a lot of different formalisms. You can talk about summing the forces and getting accelerations, Newtonian dynamics. You can talk about Hamiltonian mechanics. You can talk about Lagrangian mechanics. Well, it turns out that of all those options, the Lagrangian approach, which is fundamentally based on an action principle, is going to be our best friend. And there's a couple of reasons for this. One thing that you should be comfortable with from intermediate mechanics is that if I defined an action as the time interval of a Lagrangian, where secretly this Lagrangian is a function of generalized coordinates and their velocities, then what we know is that if I insist on zero variation of the action under a deformation of the path with some prescribed set of boundary conditions, then this gives rise to a set of conditions which we write as partial L partial phi minus d by dt, partial L partial, sorry, not phi, q dot equals 0, which you all identify as the Euler-Lagrange equations of motion. And then you can solve these equations of motion subject to whatever boundary conditions you want to impose, and that will give you the classical evolution of the system map.
We always going to assume no explicit t-dependence in Lagrange.
Yeah, for reasons you'll understand in just a moment, but this is not even what we're going to work with. Okay? So, how many of you saw this in intermediate mechanics? Raise your hand. Sweet, I see pretty much all the hands in the room up. Okay. Now, why is this a useful starting point for us? Well, it's useful for a couple of reasons. First of all, it generalizes nicely. So we can take this non-relativistic version and we can make it relativistic in the special relativity sense. In part, if we just stop treating time like it's special. So if instead of integrating over time, we integrate over space-time, the measure of which we call d4x, you can think of that as dt, dx, dy, dz. You can take the action and you can generalize it to relativity, naturally. It's kind of hard to generalize Hamiltonian mechanics to relativity because the Hamiltonian framework explicitly picks out time as the conjugate variable to the Hamiltonian. So how are you going to relativize that? Lagrangians, no problem. You can take the point particle starting point, which is what you were working with in your intermediate mechanics class, and you can turn it into a field description. And when we do that, normally the canonical coordinate, the generalized coordinate, which tells us how the particle is moving as a function of time. So by the way, the Q's could just be like X, Y, and Z. But they can be more general things, which is what makes Lagrangian mechanics so powerful. Like you could have a roller coaster, and your Q coordinate could just be the distance along the track, which is a weird combination of X and Y if you put an X, Y coordinate system down, but you could more easily describe it in terms of position along the track. So those kinds of generalized coordinates really make Lagrangian mechanics powerful. But we're not interested in following particles. Well, we're not so much interested in following particles along their trajectory, but rather we want to talk about what field configurations look like throughout space-time. So to go from particles to fields, we just replace generalized coordinates with field variables, which are defined everywhere throughout space-time. And then lastly, if we want to go from classical mechanics, which is sort of rooted in this framework, to quantum mechanics, we take the action principle, which says you consider the variation of S and set it equal to 0 to find the equations of motion you solve for the unique evolution. And for those who went to Physics X last Friday, you know that this principle gets replaced with what? The simpler version of that question is, what did we talk about last Friday from noon to 1?
Path integral?
Path integrals, yes, thank you. Okay? So to go from classical mechanics to quantum mechanics, we just replace the principle, but it's still a principle that's constructed from the action S. Okay? Another reason why the action is a good place to start is that it allows a very natural way to realize the symmetries of a system. For example, if you want to impose rotational invariance in your physical system, you just say the Lagrangian needs to be a scalar. Or in a relativistic context, if you want it to be invariant under boosts and rotations, you want it to be a Lorentz scalar. Okay, and we're going to find the sort of manifest appearance of symmetries to be a very crucial part of developing these theories. So actions are just, they're the way to go. All right? So now what I'm going to do very quickly is something that's it's half of a review, but it's going to be a different context, and so parts of this will be recognizable, but parts of it will be new. So first of all, how does an action principle actually work? Well, the first thing to realize is that an action of any form is a functional. How many of you have heard the word functional before? Okay, somebody tell me what a functional is. Levi, what's a functional?
It's kind of a function that depends upon, I guess, other functions.
Yes, it's a function which depends upon a function. Conjunction, junction, what's your function? Hook it up. You guys need to go watch those old educational videos. Anyway, so a function we know is something where if I give you a value for x, you get a number. So an example of a function is that. You give me an x. I'm glad I wrote an example in my notes because I would have gotten it wrong. Anyway, so this is a function. A simple example of a functional is an expression like this. So s of f of x. So we say a function of x, we say a functional of functions. Could be something like integral f of x dx from 0 to 1. And you'll notice you can't evaluate this until you are given the function. But if I give you a function, say f of x equals x squared, then you can evaluate this. So a function takes you from your variable to a number. Here a functional takes you from a function to a number. Okay, where there's bounds on this, so it just gives you a number after you integrate. Okay? Now, we know that the utility of functions in calculus is that you can take the derivative of the function and set it equal to 0, and so you can find which values of x extremize a function. So if you're looking for maxima or minima of a function, you just take the derivative and set equal to 0. Here, we can take the variational derivative of s with respect to the functions that are its arguments, and if we impose that that vanishes, then this gives us the function which extremizes s. So it's perfectly analogous to the way we handle functions in calculus. It's just now our functions are functions of functions, hence the new name, but we can still extremize them in the same sense. These derivatives are a little bit more complicated than those derivatives, but yes, Rochelle.
So like a functional, like I don't, like maybe we'll be using this in this class, but like don't they need like inputs that are the variables and the functions, not just the function?
Inputs that are the variables, you mean the variables upon which the function depends? Sure, yeah, definitely.
So like the integral case there is a special case of a functional that,
This is just an example of a functional.
but it doesn't require a variable input.
Well, no, we're specifying what x is. I mean, we have implicit in here that we're talking about the real line on the interval from 0 to 1.
Sure, but you're not specifying an x value. I mean, obviously, but yeah, sorry.
Yeah, no, well, I'm specifying a range of x values. But in all of this, for example, I'm kind of implicitly assuming that we're talking about a function of a real variable. This could be a function of a complex variable, in which case you need to worry about, what values this is taking through the plane. So yeah, you're right. To completely specify it, you need to give the variables and then the form of the functions and so forth. So. Okay, so what we're going to do is we're actually going to look at this and see how the equations of motion follow for the case of relativistic fields. Because even though this point particle Lagrangian mechanics coming from actions like this that you studied in 350 can be generalized to relativistic point particles. That's not so useful for us because relativistic point particles have a lot of issues that come about because of creation and annihilation of particles, and so it's easier to just jump straight to a starting point in terms of fields, because fields naturally accommodate the creation and annihilation of particles. So here we go. So I'm going to generalize this to an action based on the integral of what is now going to be a Lagrangian density, which is a function of the fields and their derivatives integrated over d4x. So what I have in mind is, let's take this starting point and let's replace Q with the field. So remember earlier I said that to go from point particles to fields, we replace the generalized coordinates with the field variables. The generalized velocities get replaced with d phi dx mu. D by dt is not special in relativity because time is not special. We should take derivatives with respect to all of the coordinates. This d phi dx mu is abbreviated as d mu phi. And then the dt we should replace with the d4x. Okay, so I'm really just making all the generalizations I talked about earlier and taking this expression and then repeating it. And then just to clarify that we're not working with a Lagrangian anymore, we give it a script L. Okay? And there's an additional technicality that this has to be a Lagrangian density because this has a non-trivial transformation under volume scalings, but we're not going to get into the details of that. You can take general relativity if you really want to know. Yes?
I thought the Lagrangian was already a script L.
I feel like it's in the script.
Yeah, well, in the Flournoy approach where I just need a different letter. So Lagrangian densities are always written with a script L. I would like to see that reference, and then if they treat continuum fields, how they reference a Lagrangian density, because they're going to need another L. Folks, we need another L. And I don't know of another L that's simple. Okay, so let me bust through this. Those who have attended the last couple of physics X's know what this story roughly looks like, but here we go. So you might say to yourself, well, if you've got an action and we're going to do quantum mechanics, really you should be stuffing this into a path integral, which, by the way, I haven't really defined for you. And it's true that eventually we will have to kind of beat on a path integral to get useful quantum mechanical results, but it turns out that we get a lot of valuable information just from the classical equations of motion that come from this action. Okay? So we're going to start by going through the usual classical procedure of finding the equations of motion, and then later in the course we'll talk about the quantum bits of what we're doing. So what we're going to do is consider a field configuration phi of x mu, and you can literally think of this as a function phi which is defined everywhere in space-time. So it's got a value at each point x mu, where x mu has x, y, z, and t components. And a region of space-time I'll call M, with a boundary dm and boundary conditions phi x mu on the boundary. So I'm going to tell you what the field values are on the boundary, and what we want to do is figure out, given those boundary conditions, what does the field look like everywhere else. So you can think of a region of space-time as a hoop in time, and you're specifying the field on the hoop in time, and then you're just filling it in by getting some equations of motion to solve. Okay? Here we go. So now let's deform to the following. Phi prime x mu is the one we started with, plus some variation So I start with some fiducial field configuration. I could, for example, just assume everything is 0 everywhere. And then I create a new field configuration by varying this thing, but I can vary it differently wherever I am. I can kind of wiggle it differently at different points. But I want this field configuration to also satisfy my boundary condition. So I want phi prime on the boundary to be the same as phi on the boundary. And Branham, where are you? Branham, you're going to be happy to tell me what this condition imposes on the deltas.
Zero at the boundary.
Exactly. Exactamundo. They have to vanish on the boundary. Okay. In 350, when you derived Lagrangians equations from a start action, you said that you considered paths with 0 variation on the endpoints. That's exactly analogous. I want field configurations that are deformed, but the deformations vanish on the boundary. Okay?
Alex,
Yeah.
do you make any statements about the size of deformations? Like, do they have to be perturbated?
Huge! No, we'll consider this. We'll consider them small, because I'm going to do a first order analysis, but yeah, so you would have to actually explore the global structure based on whatever your Lagrangian is to see if there are different isolated extrema. So there is sort of a size constraint on it. So smallish that I can get a leading order, a linear approximation. Okay, so here we go. To leading order, the variation of S is given by the variation of the Lagrangian integrated over d4x, and then we can break up the variation of the Lagrangian into contributions from phi and d mu phi as follows. We can take the partial with respect to phi and then consider the variation of phi, and then we can take the partial with respect to d mu phi and consider the variation of d mu phi. All right? And then what we want to do is impose that that variation is 0. So we want to extremize this. And then now we just follow the standard story for massaging this a bit into a form where we can recognize Euler-Lagrange equations. So here we go. So we're going to take this term and do what with it?
Product rule?
I like it. I like it. You want to say integrate by parts, but no, let's just, well, yeah, we're going to integrate by parts. Oh, with the product rule, okay? So with the product rule, what we do is the following. We say, this thing has a derivative that I would like to pull out as an overall derivative. So if I consider this quantity, so this is a total derivative. If I hit the first term with this, then I get d mu, or d by dx mu, partial L partial mu phi, times the variation. And then I let the derivative hit the second term. Shit. Okay, so quick note, partial derivatives commute with the variation of the path, so I can actually move this derivative inside the delta and let it just act on phi, and so I can write this as d phi dx mu. And you'll notice that this term right here is exactly this term. So I can replace this term by this minus this, and if I do that, what I find is that this is going to become the integral of partial L partial phi minus partial with respect to x mu, partial L partial d mu phi, all times delta phi d4x plus the integral of d by dx mu of partial L partial mu phi delta phi e for x, also known as integration by parts. Okay? So if you're not aware, integration by parts is just using the product rule backwards. Okay, but this thing is the integral of a total derivative. So that means that this guy is really just the integrand evaluated on the boundary. But what is that thing on the boundary? It's like my clap today. See, that was weak, but my clap earlier was, anyway. Oh no, sorry. I'm looking. Were you in the studio? No, it was Tom Henry that said it. Yeah, I was in the studio and I clapped, and it was so loud, and everybody looked, and I said, "Wow, that was an unusually loud clap." And Tom Henry made fun of me for modest bragging, I think is what he said. Anyway, it doesn't matter. It doesn't matter. What's delta phi on the boundary? It's 0. So this whole term we can ignore. Okay? Alexandria, is that bothering you?
Oh, no, this is a lot of writing.
Oh, it's a hell of a lot of writing, but it's all going to appear in the notes. You know how that goes. Well, you don't have to write this one. You can just put a 0.
There you go.
Okay, so at the end of the day, we want this thing to equal 0. But we want this thing to be equal to 0 for an arbitrary deformation of the path, except that it has to be 0 on the endpoints. So what I mean is I want this to be anything. In particular, I want to allow it to be non-zero. Well, if this whole thing has to be 0 without any constraint on this, what does the thing in the brackets have to equal? 0. Okay? So then, being clever with my time and energy, voila. There are the Euler-Lagrange equations for a relativistic field. Okay? And what I want to do is draw your eye to the comparison. You could have actually guessed it. If we replace q with phi, replace derivatives with respect to t with derivatives with respect to all the coordinates, and then replace q dot with the derivative with respect to phi, you could have just written this down from the start. Okay. So I know you've probably not seen the action principle in the equations of motion derived for a relativistic field, but really and truthfully, the steps that I just took are almost identical to the steps you would take, or that you should have seen in Physics 350 when you were just working with good old Lagrangians for non-relativistic point particles. Yes, ma'am?
So we changed like what the action was. So how do we still know that the new action is we still want it to be stationary?
Well, I guess the way you think about it is that is something to be determined, actually. So how do we know that an action principle works in the first place? So the way that we know it is we write down the Lagrangian for a system that we already trust Newton's laws being applied. So we write down a Lagrangian that would reproduce Newton's laws. We stuff it into an action principle, demand the variation equals 0, and the Euler-Lagrange equations that come out are actually Newton's laws. So here, we're taking the bold step of saying, well, if I generalize my Lagrangian to a Lagrangian for relativistic fields and impose an action principle, get equations of motion, do these reproduce equations of motion that we already know? If they do, then this approach seems like it's on the right track, and I'm about to show you that it does. Okay? So yeah, I mean, you've got to find support for the action principle, but so far, action principles seem to be the way to go because they reproduce pretty much all the physics that we really care about.
And they also predicted new things that happen?
Yes, they do. They absolutely do, especially when you get into quantum mechanical context. Okay, so now that I'm erasing exactly the equation that I need, let's push on. So a couple of qualifying statements, and then we'll get into examples. Okay, here we go. So this might go a little fast, but I'm going to be repeating myself 3 times. So if you don't catch the first round, you'll probably catch one of the latter 2. So first statement is, when constructing a Lagrangian, you are used to t minus v. Okay? And this in part is fed by the starting point of h is t plus v. Okay? And there's a lot of machinery that goes in connecting the Hamiltonian and Lagrangian frameworks. But anyway, this is how you're used to writing down or constructing your Lagrangians. What we're going to do in this class is we're going to think of this in slightly different terms. We're going to think of the Lagrangian as a Lagrangian for the kinetic energy of the system. Okay, very similar to that term. And we're going to think about a second piece that describes the interactions of the system. Of course, that's what the potential term does in the original Lagrangian. But since I'm not starting from a Hamiltonian framework, there's no reason to adhere to this sign. So for now, I'm just going to put a plus here. And that's completely fine because I haven't really told you what these terms are or how we're going to get them. Okay? So when I write kinetic plus interaction, I'm not just abusing, hey, you're supposed to have a minus sign there. We're not going to be getting our Lagrangians in the same way you got your Lagrangians in the classical point particle case. Okay? So if I have a Lagrangian which only has a kinetic term, there is no interaction terms, then we would call this the free field Lagrangian. Okay? That is, it's just the Lagrangian describing a field that's not interacting with anything. It would be an ostensibly boring theory. Seems like you would need interactions to get something interesting to happen. Okay? Now here's the incredibly insightful statement, which we will see borne out in detail. We are actually going to create this term by starting with this term and imposing a symmetry. And that is actually how we're going to explain all of the interactions in the standard model. By starting with kinetic terms and saying, I want this particular symmetry, and then these will pop out. I'm not going to talk about that today, but it's going to be coming in the next couple of weeks. Okay? So for starters, I'm going to focus on just kinetic terms. And then eventually we will start adding in these interactions. Okay? So for kinetic terms, you're used to expressions like p squared over 2m, or 1/2 mv squared. I don't know why I wrote p squared over 2m. That's terrible. We don't work in terms of momentum when we do Lagrangians. So there you go. There's your classic kinetic term in a point particle classical Lagrangian. Is this going to work for relativistic fields? No. First of all, we can have massless fields in relativity, so that term is going to really screw things up. And secondly, we don't have velocity. We have the derivative of the field. Because remember, we replace q dot with d mu phi. Okay? So when we want to write down the analog of this for relativistic fields, we expect it to look quite different than this. I mean, you might think that you would say 1/2 m d mu phi squared would be the relativistic field generalization of this, but what I'm telling you is it's not going to be that simple, partly because we want to be able to deal with massless fields. Okay? But also because so far, although I haven't named it, this thing right here is secretly just a scalar field. I haven't put any indices on it or said it's a spinor, so there's no reason to think it's as much. We're going to want to be able to write down Lagrangians for scalar fields, but also vector fields, and of course, spinor fields. Okay? So when I do this, I'm going to give you basically the kinetic Lagrangian for each of these. It might not be intuitive what I write down to start with, but given that, we're going to apply the Euler-Lagrange equations of motion, or sorry, we're going to beat out the form of the Euler-Lagrange equations of motion for each of them. So just a reminder, those are partial L, partial, we'll just call this the field, minus partial x mu, partial L, partial d mu, whatever, equals 0, where the question mark I put in there because it might be a scalar phi, it might be a vector, it might be a spinor, so we want to allow all possibilities. Okay, so again, I'm going to write down some kinetic terms for these three different varieties of things, and then beat out the equations of motion. So, starting with a scalar, the free or kinetic term, I'll call it the free term because the word free is shorter to write than the word kinetic, can be written as 1/2 d mu phi plus 1/2 mc over h bar quantity squared phi squared. Okay?
So these are the free field equations of motion we're beating out?
Yes. These are the equations of motion for the fields when they're not interacting with anything. So they're boring, okay, but they're going to be our starting point. This is clearly something like your velocity term, because this is the d mu phi, which we said would be the replacement of q dot. So this is kind of like v squared, except there's no m. The m comes here, and it doesn't multiply derivatives of the field, it just multiplies the field squared. Okay? Well, one way you can think about it is, if the field is sort of 0 everywhere, and then I create a little hump in the field, I want this thing to have mass, and in particular rest mass energy, even if it's not moving. Okay? And so I'm going to have a contribution proportional to how much phi is excited from 0, and that's what this term is capturing. Okay? The other nice thing about this expression is that it is immediately generalizable to 0 mass fields, because I just ignored this term. Okay? So now I want to take this and cram it into here. Here we go. So partial L, partial phi. Now remember, I'm treating d mu phi and phi as separate. So in the first term over there, partial L, partial phi is just going to be mc over h bar squared phi. Okay, it's a quadratic in phi. And then partial L, partial d mu phi. So the inner term of this, we'll come to the last derivative in a moment. Well, this is essentially d mu phi squared, and so this is just going to become d mu phi. And if you're worried about, well, this has got a lower index, this has got an upper index, what do I do about that? There's a formal way to handle that by going back in and putting in a factor of the metric or the inverse metric, pick your poison, and then carefully following the contraction of the indices and matching it up with what you're taking the derivative with respect to, and you'll find at the end of the day it actually it does simplify to this. Now you might say, well, what about this Flournoy? Why didn't I get that one? Well, remember, on this expression, this is honest. Oh, actually, I'm sorry, I lied. It is d mu phi. This is lower in the bottom, which means overall this index is upper. Okay? Does that make sense? So if I have 1 over x mu, altogether this has a lower index. And if I write 1 over x mu, altogether this has an upper index. So this is lower in the bottom, so overall it's upper. And you literally don't have to take my word for it. You can follow all the fun gymnastics. So if I take this and I plug it in there, so I'm going to take another derivative, and then I combine it with what I got from there, I find mc over h bar squared phi minus d by dx mu of d mu phi, and that is secretly just d mu phi. All that's equal to 0. Which you all recognize as? The Klein-Gordon equation. Maybe that was a joke about recognizing it. So this is the wave equation for a massless scalar field. A relativistic scalar field. It doesn't have to be massless. If I ignore this term, it's the wave equation for a relativistic scalar field. Okay, so that's our first result. Boom. Let's skip spinors and go on to vectors. So I'm going to have a vector field A mu come next. Its Lagrangian, or the free non-interacting Lagrangian, is going to be the following: 1 over 16 pi f mu nu plus 1 over 8 pi mc over h bar squared a mu, where f mu nu is defined as d mu a nu minus d nu a mu, and f mu nu is defined as eta mu lambda, eta nu rho, f lambda rho. So the vector field is this A. It's got an upper index like all vectors do. But it turns out that we really need to form this thing out of it. Okay? So we can lower the index on A, take some derivatives to get f lower mu nu, and then to form f upper mu nu, we can use the inverse metric to raise the two indices here. Okay? So this term here is hiding factors of this. Now notice, this term is involving derivatives of A squared. So it's a lot like this term. It's a velocity squared. And this is just something times A squared, just like the mass term here. Ariel.
This is true for any vector field, not because this looks like a EM.
It's true for any vector field. Okay. So there's, first I want you to note the similarities between this and this, bearing in mind this is a somewhat more complicated expression because you got to build all this. Okay? And I should say that in the next lecture I'm going to make the connection between all of these different things. So even though they look very different, there's actually an important underlying connection. Okay, so now we take this, we shove it into there. So the first part is easy enough. Partial L, partial A mu is just going to be, bam, it's a quadratic. And so I'm going to have 1 over 4 pi mc over h bar squared A lower mu left. Okay. And then the next part is where it gets a little tricky. Partial L, partial nu A mu. Hold on. Sorry, I'm going to vary this with respect to lower mu, so I'll be left with the upper mu. Only because I'm going to do the derivative of the dual vector here, and I want to have the same thing here that I have here. Okay. Evaluating this is actually a little tricky. Okay, it requires some careful index following. So you know why you're going to understand that really well? Because you're going to do it in homework. But what you can demonstrate after a bit of massaging is that this is just 1 over 4 pi f mu nu. Again, the two lower indices in the bottom become upper indices. And you don't have to magically do that, it comes out. Where this f mu nu is exactly that guy. And so if I put the two results together, I have, remember this goes in here, so I have a derivative acting on it. So I have d mu of 1 over 4 pi f mu nu. 1 over 4 pi d mu f mu nu minus mc over h bar squared a nu equals 0. From just combining the derivative of this with this. Notice all the indices are taken care of. The mu is summed, so it disappears. So this term only has an upper nu. This term only has an upper nu. So technically, if you wanted to be picky, you'd put that an upper nu. Okay? And we recognize Well, we recognize that with m equals 0, so if this term is 0, then these just become d mu f mu nu equals 0, which is Maxwell's equations. Well, it's half of Maxwell's equations. In particular, it's del cross b minus partial e partial t equals 0, and del dot e equals 0, where we recognize if we actually work out what F mu nu is and think of this as the usual vector potential from E and M, F mu nu is 0 minus E1 minus E2 minus E3, B3, B2, B1, zeros down the diagonal, and then you anti-symmetrically flip that. So the F mu nu is really just a collection of E and B fields, something which you should see in, if not intermediate, then advanced E and M. And so if you took this expression and plugged it in here, you'd realize you're starting to get Maxwell's equations out, but you would only get 2 of them. You wouldn't get all 4 of them. Okay? In particular, you would get the source full versions, because this is the place where you would normally put in a current density, and this is the place where you would normally put in a charge density, but there's no current and charge because there's no interaction here. By the way, if you wanted to think about electromagnetism where the photon had mass, you would just go back to this equation. And that's how you would describe electromagnetism with a massive photon. The other 2 of Maxwell's equations correspond to the electromagnetic geometry. So these are actually a set of conditions that come about as a restriction on the gauge bundle. It's called the Bianchi identity and blah, 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 blah. So we're not going to worry about it. But the important thing to note is that you only get half of Maxwell's equations from an action principle. The other 2 you cannot get from an action principle. Yes?
Is it that the second one, the second term would be 1 over 8 pi F mu nu?
This one?
Yeah.
Why should it be 1 over 8 pi?
Well, I mean, if there's a 1 over 4 pi in front of both of them, then. It's just when you rewrote the final equation.
Oh, when I rewrote the final equation, I dropped the 4 pi. Oh, no, sorry. No, this is actually where I have an error. There should be no 1 over 4 pi there. So, you have the 1 over 4 pi in front of each term, and then you drop the 1 over 4 pi because the whole thing's equal to 0. Okay, I got to get through this. The spinner case is actually pretty short, so let me bang through this really quick, and then I'll send you on your way. Ready for the awesomeness we'll encounter next time. So here we go. What is a spin? What is a spinner? What does a spinner free Lagrangian look like? It looks like the following. This is going to be weird. H bar, C, psi bar, gamma mu, d mu, psi, plus mc squared psi bar psi. Okay? This term should feel okay. It's kind of a square of the spinor field times a mass. That's similar to what we've been writing. This term is weird. It's the field times the derivative of the field. In all the other equations we've written, or all the other Lagrangians, it's been the derivative squared. But for spinors, you do one derivative and multiply it by the field. We will eventually understand why this is the case, but for now, let me just take this and bang it through that machinery. And what we're going to discover is that there is going to be need to treat these psi and psi bar independently. So we can vary with respect to psi, or we can vary with respect to psi bar. And if we vary with respect to psi bar first, this is actually easy because the variation gives me d by d psi bar. Well, there's a psi bar there, so I get everything that's multiplying it. And then there's the sidebar there, so I get everything that's multiplying it. And that's all equal to 0. And I missed something. Oh, no, I'm sorry. Sorry. I'm taking the derivative with respect to sidebar. So I have a contribution from here, everything that's multiplying that, and a contribution to this term from this. So that's equal to 0. So this term doesn't contribute because the Lagrangian has no derivative with respect to sidebar. So this doesn't give me anything. I get everything from this. On the other hand, and this is pretty cool, if I vary with respect to psi, now there is a derivative. So when I do the dl d psi minus dx d mu partial L partial mu psi. When I do this term, I get a contribution not from here at all, but from this term. Okay? But now I pick up a term from this guy because there is a derivative with respect to psi in my Lagrangian. If I take the derivative with respect to the derivative of psi, I literally just take everything that's multiplying this. So that's this term. But then I take the derivative of that. And so at the end of the day, this is going to be minus d mu h bar c sidebar gamma mu equals 0. And the final observation that I'll make is this combination gamma mu d mu, which happens a ton in everywhere throughout this course, we're just going to give it a nickname. We're going to call it d slash. So I can rewrite this equation if I divide by both sides by h bar c. That's a d slash. D slash. If I divide through by h bar c, then I've got d slash psi plus mc over h bar psi equals 0. Okay? Well, I can pull this gamma mu to the other side of this. There's no reason why. Gamma mu is a constant. So I can pull it to the other side of this and make this into a d slash that's now acting on psi bar. If I divide through by h bar c, then this equation is just going to become d slash psi bar minus mc over h bar psi bar equals 0. Okay? So it's funny because even though getting the equation of motion looked quite different in the two cases, you know, in this case I only use this term, in this case I use both, they actually end up giving you pretty much the same equation. What's even weirder is you vary with respect to psi bar and end up getting the equation for psi. You vary with respect to psi and get the equation for psi bar. Okay? Does anybody know what this is called? Smart ass, only in mine. That's the Dirac equation. This is the conjugate, or the adjoint Dirac equation. So what we have discovered is that the Dirac equation, which some of you might or might not have heard of before, the Dirac equation is actually just the equation of motion for a free, non-interacting spinor field. Now Dirac did not derive this thing from a Lagrangian starting point. He actually derived the equation of motion directly. And what's strange is he was trying to derive it by taking the derivative, or the square root of the Klein-Gordon equation. In line with this whole philosophy that spinors know about the square root of things. So he literally took the Klein-Gordon equation and said, well, how can I take the square root of this? And this is actually covered in a lot of books if you want to look it up, but he arrived at this equation. Okay? But of course, we're going to be starting with action principles, so we're going to start with the Dirac-Lagrangian. And we're going to give these equations and this starting point an interpretation next time by looking at how it's related to the Klein-Gordon equation. By the way, Dirac, one of the funniest characters in all of physics, my favorite story about Dirac is that he was rushing to get out of the physics building one day, and somebody asked him, where is he going? And he said, I've got to run. Wigner's sister is pregnant and about to deliver her baby. No, is that Wigner's sister is pregnant and is about to deliver her baby. Wigner, you guys know Eugene Wigner, the great group theorist, early quantum mechanic. So that was his response. Wigner's sister is pregnant and about to have her baby. Not conveying the fact that that was in fact Dirac's wife. The baby. So anyway, okay, all right. That's it for today. Thanks for sticking it out. More on all of this next time.